Right, so now let's take a look at allocate. So we are going to need to write tests for this, so let's go ahead and do that. So test body allocate. Sure. Just going to go up here, get these. Sure, put them there. So we still have 128 bytes of memory length and min size of 1. Yeah, no, that's fine. That's pretty okay. So case 1, what would that be? I think case 1 would just be allocate the full memory. Right, so we are going to ask for 128 bytes, and we hope to get a slice that starts at 0x1000 and has 128 bytes of length. So that would be body.allocate, and it takes a requested size that would be 128, and it returns const allocated is a slice of U8s. Right, so with this slice of U8s, we are going to basically just do the outtry set testing. Expect equal. So we expect 0x1000 from allocate.pointer. Allocated, sorry, .pointer, and we expect 128 from allocate.length. Right, so let's start by trying that. Actually, I'm gonna need to make this a bit bigger. So we were in kernel source, and we do zig build tests. Okay, so expected U size found. Okay, right, I see. So this one expected the U size ID, and it found a node index which is of type U64, I guess. Yeah. Right. So this would need to be that dot value, I think. That should do it. So where are we? So cannot dereference non-pointer type. 26. Cannot dereference non-pointer type. Oh, right. Okay, because we have never tried this. Cool. So what now? Try self alloc. Expected type U8 found error out of memory. Where is that? Oh, right. Okay. So this one needs to have that. Cannot assign to constant. That's fine. Where was that defined? That was defined around here. So get that there. Expected U size found body whatever. So that should be here. So this one becomes dot value. And so where was this? 132. What? Expected 3 arguments found 2. So self bucket index O. Right. There we go. Clear and test. Cool. So 223. Right. So try. Okay. incompatible types, comp int and a pointer. Okay, so that's fine. So pointer from int. No, int from pointer. There we go. Okay, so we have an integer overflow in 136. So what is bucket? Bucket is we don't have its type, but we should know its type. Its type should be this here, and it's a bucket index. All right. So let's add a few prints. So instead debug.print, and we are going to print. First of all, let's start by doing this. Requested size is D. Line size is D. And here we are going to give it requested length and what do we call that length? Right. So now here we are going to print the matching bucket. So matching bucket for size D is sure. This would need to be so length and bucket. All right. So okay, so hold on. First of all, just going to add new line here and here. And now we can at least read this. So request size and line size should be the same. That's fine. Matching bucket for size. This is 0. Whereas, is that the convention we went for? No. No. Should have matched the very last bucket. So max order -1 is what it should have matched. So we might have a problem. Length to bucket index. So I think we are starting from max order -1, which is the highest order, rather the yeah. So here we should probably start with 0 and do +1. I think. Okay. So, what is this? So, starting from 7, that should be fine. And here we have other things. So, value. Computing the parent of this is a problem. Right, so we need to add a kind of special case for should probably do this. This should at least avoid us having that error. Right, so now we skip this entire loop. But if we do because the main problem is this, the computing the parent, I think this one here. Since the root node has no parent, it's the parent of all nodes, we should treat it as a special case for now. Sure. So if bucket is max order, if we should also check whether we could just do this. If maybe node captured as node, then we basically do this. And we do these. There we go. We are also going to need a node index. Right, so make that constant, and that should do the trick. What's going on here? 112. Otherwise, in this case here, we are going to return error out of memory, something like that. Just gonna make sure that this is the test that fails. Okay, so it's not this test that fails. So which is the test that is failing? Body test. Okay, so it's this one. Right, so I think we need to invert the indices we are expecting here, because we so hold on, let me do this. Let's think about this for a second, okay? So here we are checking that node index from pointer for a bucket index of 7 at this address here should be 0. That's fine. For 6, that should be okay. For 5, that also should be okay. Right, so all of these are pretty much okay from what I see. Right, so now let's check other things. So all of these are okay. I'm actually confused as to where is the problem, so let's see. Expected 1 found 6 in test or body test. Is it this one here? Oh, right. Okay. Yeah. Yep. Okay. So I'm not confused anymore. Cool. Function with non-void return in 154. No, that's fine. So now this should be this failing. The other should pass. Okay, cool. Right, so now we are asking it to allocate 128. We match the bucket. The bucket is, I'm not sure we've seen it. Let's get rid of this. Let's put all of these back and rerun our test. Cannot assign to a constant. Well, first of all, why are we in the while loop? Shouldn't we just get right out here? Oh, I'm missing something. Right. Yeah, okay. I see it. Actually. That's just a compile error, actually. Never mind. Right. Okay, so now we do have our test that runs. Let's see. So, the test actually succeeds. So if we, let's do something like this and see it fail, expected 128, or expected 129 and found 128. That's fine. That's pretty cool. Right, so this case here succeeds. Let's just get rid of these for now. Actually, let me just get rid of that defer. Okay, so now we are going to go ahead and take a look at the other cases. So case 2 would be allocate 8 bytes. Let's annotate this way, from a non split memory. Okay. So that means that here we are going to need to re-init our body. So let's get rid of this. Let's do body.d-init, and let's recreate body is try.init with test alloc. Right, so for the rest, I'm just going to get rid of this. I'm going to copy these. And I'm actually going to make this a variable, get rid of that. And here we are going to just ask for 8 bytes. Right, so 8 bytes from a non-split memory. That should be this address here, and this here should be 8. Oops. So wait a minute. So request size is 8, align size is 8, that's fine. Matching bucket for size 8 is 3, or max order 8. That's actually fine. Now we are going to need to take a look at our while loop. So let's take this here. Let's do pop node is any, and let's not forget to put a new line at the end. And here we are going to do maybe node. Okay. Here we are going to put that here. Otherwise, we are going to do that. here we are going to write no node found at bucket d here bucket. Oops. Right, and this one here we'll need to get rid of that and do node. Sure. Let's try for that. Actually, hold on, before we do any of that, I'm just going to go here and add this. Cool. So pop node null. Okay, well, that's a problem solved. But this one here is not okay. Hold on, let's check. Let's recheck the initialization here. Okay, so this one here shouldn't we just do also buckets? Can't type for shit today. Well, I guess that's fine. So we are still going to need to re-init the buckets. Right, so let's actually do something like this and do bucket is equal to just a new item. Pointer capture of non-pointer type. What? Okay, that did not go too well. Actually, let's try something else before we do this. Let's go all the way here and just do a check. Let's try stud testing expect equal. Actually, we should do that here. So body dot how do we go about this? Dot buckets at 7. Yeah, okay. Dot first. Head. And let's just do something like this. And it's going to complain, but that's actually pretty fine. Okay, so it's the typing that's not matched. So let's do int from pointer sure. Okay, so we expect equals, but we have memory address leaked. What is going on here? Try create right, hold on. Let's actually do this. Well, no. Here's what we are going to need to do. We are going to need to create a block, put this here in a defer inside that block. And of course, put this back as a constant. Put this inside the other block. Defer the body.dinit inside here, and create a const allocated here. That should be fine. And remove this, of course. So now let's redo this. Okay, so okay, so expected this but found this. And that's actually okay. But if we do stud.debug.print body any, is that going to be of any help? Okay, let's see. So body has memory start, that's fine. Alloc is that, and I'm looking for yeah, I don't see them. Buckets. Let's do body buckets. Okay. So the very first one is null, null. All of them are null. Okay, so we probably have a problem. Okay, so here's what we are going to do. Let's try to avoid the problem instead of solve it. Test body, yeah, so see ya, buddy. Okay, let's get this. Let's put this here. We're not solving the problem, we're avoiding the problem. So expected type body. Okay, so let's remove our this here needs to go. Right, so expected type body memory start, but found const body memory start. Right, that's fine. So this one needs to be no, not this one. This one here needs to be variable. Okay. Finally, we are getting somewhere. Right. So now let's take a look at our second thing here. First of all, I'm going to print the buckets. So for body, sure, dot buckets, capture that as B, and just gonna do so debug print any. No, that's not what I want to do. That, and we should do something like B. Yeah, sure. So now that we have that, we should be able to see clearly what the problem is. Okay, so here in the very last item here, so 0, 1, 2, 3, 4, 5, 6, 7, in the 7th item, we have a node, so that's fine. Yeah, so we should find a node at bucket 7. Now the question is, why are we not finding a node at bucket 7? Let's investigate that. Oh, hold on a minute. Yeah, maybe if we used the actual correct thing, we'd find it. Okay. Pop node here, node is that, but we still have a integer overflow here. So we are not going to avoid this problem. So in parent, we need to handle a special case where if this goes to 0, we should just get a 0 instead. Rather, let's see if this solves it, but yeah, actually, the operation itself is, so let's see if we do this, so value or 0, and then we just get rid of that. Okay. So now the problem is that I'm not sure about this now, because it means that if we have a value b1, we still get 0 actually. Yeah, so that's fine. I guess that's fine. Actually, now that I think about this, should probably avoid doing this entirely because it's so how do we go about this? So here we toggle the parent, right? So we want to do this only if the parent does exist. Otherwise, we are going to be toggling the parent of something that's not related to us. So let's actually make this a const parent node index, sure. And this would be node index dot parent dot value, rather just that, right? And we can check that if actually let's make parent be able to fail. That's actually okay. So if so self dot value is 0, right? Return error no parent. Yeah, and I'm just going to do this. And add this. Yeah, cool is fine. Because that should not happen in the normal case. So what is the problem here? Found, okay, so 151, yeah, of course. So let's do catch now, so what I want to do is actually do something otherwise. Catch continue. No, that's not what I wanted to do. Right, so what we need to do is actually get rid of this and do if node index.parent and catch that as parent node index and do this. Yeah, that's pretty much all we need to do. So this one here would be parent node index.value. And I'm going to get rid of this. Cool. Same should go for this one here. So if node index.parent get that as parent node index do this. So parent node index.value. Otherwise, we just don't do it. Expected optional type found error type. I thought we could do this for errors too. Yeah, so I thought we could do that for errors too. So, yeah. Oh. Is this needed then? Okay, so I guess we need to catch the error somehow and then just do nothing with it. And of course it's going to say it's news, but I guess that's the syntax. Okay. Okay, so let's see here. So expected this found that, but why is that? Okay, so now that we have no node found at that, let me just do actually this found node at bucket D and just go there to bucket. Right. Found node bucket 7, that's fine. Now, let's get rid of this. Let's declutter this a bit. Now we are going to go ahead and go into this loop here. Yeah, let's go into here. Let's do setting toggling parent node. And that should be so self.nodeState. Oops. Self.nodeState dot get. No, what's the is set, maybe, yeah. Is set parent node index. And probably do something like if no, that's not what I wanted to do. Node state. Actually, let's just do something like this. Expected use size found, whatever that is. Oh, yeah, of course. Dot value. No problems. Okay, let's make this a bit more readable. So toggling parent found node found true, true, true. Okay, so I'm already seeing what might be a problem because we are toggling 3 parents. So we are at level 7 or 7, and we should be toggling. No, actually, never mind, because order 7 is the root node, so we are not toggling its parent. We are toggling 6, 5, and 4, since we are matching order 3. That should be okay, I think. That's all right. Now, let's keep on going. So we have this thing here being toggled. We create this half node. We set it to the right child of every order we traverse, and then we go up 1 level in that order while setting the node index to the left child to that. Right. Yes, okay. That actually sounds pretty nice. And then we get here. So here what I want to know is what is our node index once we get to this point here. So node, so matched allocation, let's just call it matched node, is any. Let's get rid of this and just do node index. Let's do this and this actually, because I want to see the matching bucket and node index dot value. Sure. All right. Of course, I'm going to have to put this. Okay, so we matched bucket 3, but node index is 15 for some reason. Why is that? Why is our node index 15? Yeah, it should be 0, I think. It should be 0. So let's go here and just get this and put this in here. So let's do this and replace this with bucket. So walk-in node. Let's see where we stray. So at bucket 7 we get node 1. Well, that's already bad. That's already super bad because we should have started by having this node index here. Actually, let's print that. Let's print node index.value here. So where was that? Okay, so found node at bucket 7, and that's 0. That's correct. That should be the correct one. And then we are walking the nodes here, and its left child should still be so the left child of node 0 at bucket 7 should still be 0, I think. So here we do have a problem. we do have a problem because I think I got confused along the way and I confused the IDs of node state with the IDs of the nodes inside the bucket, their respective buckets. Yeah. Okay, well, I guess we still have some work to do then. Okay. So, we would like to change or create a notion of so what are we going to name that? Because we still need to go from bucket plus node index to what I'll call a map index. Let's actually call that node state index. Sure. And this would need to have actually no. This can just be a struct, a normal struct. We'll see. Anyway, so this one here, I'll have a public function called create. And this would take a bucket index of type bucket index. Where is that defined? So that's defined in here. Right. So let's make this a public function. Name it type. It takes a comp time. Bucket index type, which is a type, and a comp time node index type, which is a type also, and it returns a type of its own. Right, so return struct, and of course, let me just put this here. Right, so we want to have a value, or actually I'm just going to gut this thing here, except that this one here would need to go from 0 to we have actually node index type dot so how should we go about this? Bits? Yeah, something like this is what I'm thinking about. So we are going to take type info of that and check that it fits, or rather check the number of bits it has, and that's how big we should be. Right, so bucket index type bucket index type info, and let's actually we don't need bucket index type info. We need node index type info of node index type. Yeah, and this would be int bits. So that would be 1 shifted left by how many those are. Right. So we now should. So we don't really need the bucket index type. Oh, we do. Actually, we do because we need to create it from a bucket index, which would be a bucket index type. Right. Okay. So node index, which is a node index type. And this here would return this. Cool. Right. So how do we go about this now? So we should know that if we draw our tree again, let's go just 3 levels deep. This one would be bucket 2, 1, and this one would be 0, right? So we know that this one here would have a node state index of 0. Node state index, right? This one here would have a node state index of 1. This one 2. This one would be so 3, 4, 5, and 6. Right, so how do we go from bucket index plus node ID, and this one here in node ID, this one is 0. This one is, actually, hold on, let me get rid of this. Let me annotate here, node state in this corner here, and node index in this corner here, just for clarity. So this one here would still be 0, 1, and this would still be 0, 1, 2, and 3, right? So we want to map to 0 to 0, right? And then 1, 0 to 1, 1, 1 to 2, and 0, 0 to 3, 0, 1 to 4, etc., and 0, 3 to 6. Right. So this will probably need to be some max order minus bucket index, because we need to invert these. And then we should have, so this one would be, max order here is 2, I guess. No, it would be 3. So this one would be, would need to be -1. Right, so this transforms our mapping from 0, 0 goes to 0 all the way to 2, 3 goes to 6. And in between we'll have 2, 2 goes to 5, etc., right? So how do we go about this? And I'll add one more here, which would be 1, 0 to go to 1. All right, so let me just clear this up and redraw it, and we'll try to think through this. All right, so let me just go ahead and draw this up here, just like so. So I'm going to annotate the node state index top right, so 2, 3, oops, 4, 5, and 6, and here we'd have 0, 0, 1, and then 0, 1, 2, and 3. So one obvious mapping here would be So we'd like, so we have a tree-like structure where we have the first level is this one, then the second level, and then the third level, right? And every single time the levels, they basically have double the items in them. And that means that we could actually, so from a bucket index, we can select which level we are in, right? By computing the power of 2 of that level. So 2 of max order minus 1 minus the bucket index. I think this would give us the start of each level. So if we take, for example, this one here is 2, 1, and 0. Of course, max order is 3 in this case. So if we do 3 minus 1, so that's 2 minus 2, right? So that's 0. This would give us 1. So if we subtract 1 here, this would give us 0, right? And that will point us to this cell here in our node state. Let's try with something else. Let's try with 1. So 3 minus 1 is 3. Rather, it is 1. So that's 2 minus 1 is 1. And that means that we are pointing here. If we try with 0 now, so that's 3 minus 1, that's 2. To the power of 2 is 4 minus 1, that's 3. And that's 0, 1, 2, 3. So we are pointing here. So we do get the start of every level in our node state array here. And what we need to do next is just basically offset into that with our node state, node index. So if we want this node here, which should be at offset 5, if we do this, so I'm just going to call this n. So 2 to the n minus 1 plus whatever that offset is. So node index. Let's try with 0 and 2. So that would give us 2 to the 2 minus 1 plus 2 plus 2. So that's 3 plus 2 is 5, right? So we are getting the correct offset. So that should do the trick, I think. So here I'm going to create this. We are going to return value is, so what did I just say? 1 shifted left, I'm going to use parentheses for this, by, so max order. Okay, so we are going to need max order then. Minus 1 minus the bucket index. Yes. Minus 1 plus the node index dot value. No, just node index in this case. Right, so now we just need max order, and we are going to get max order by passing it here as a comp time max order, which would be a comp time int. There we go. Right, so now we are going to need to go inside of these. Just going to take this, put it above this, and then const node state index. Yep. So that would be node state index type with bucket index, node index and max order. Is that fine? That looks fine. Right, so here we are going to get rid of all of this. So hold on, let me just see how that is defined. Actually, it's, yeah, we can get rid of this. So this would be setMath int fit in range from 0 to, if I can type, from 0 to whatever that thing we've put there. Right, so now we are going to get rid of this. And that should be okay. So let's think about this for a bit. We have a value. We compute the parents. We have children and siblings. Okay, so actually, let's try something else here. Let's do public function node index. Yeah. So self is this, and this returns a node index type. So this one would need to return so as node index type, the value here would need to be, let's think about this. So we want whatever this is. So we are going to need to remove, so this would be self.value minus whatever we've put into here. Now the only problem is that we need bucket index. I think we don't really need bucket index for this to work. We just need to get rid of as many powers of 2 as we can. Yeah, it's gonna be a bit of a problem. So for now, I'm just gonna forget about that. We don't solve problems here, we just avoid them. Right, so here, now that we actually have our node index, so we are going to try to go and get, so node index.parent, yeah. So let's create const node state index out to be node state index dot create from bucket and node index, right? And then we can do node state index dot parent, that whole thing here. And then we can go ahead and copy this again down here, node state index.parent, that goes there, that's fine. Yeah, that looks okay. Actually, this one here would need to be matching bucket, just so that we don't mess things up. Okay, so where did we get this wrong? So this one here needs to go, and this one needs to go. All right, let's rerun our test and see where we messed up. First node. What? First node. Okay. Well, then I guess you can just do this actually. Clear. Where is that? 113. Okay. And then I guess we do have that in here. One, 5, 6. Okay. That's fine. No index type. Type U7 has no members. Oh, okay, I see it. It's type info, not type. There you go. I can do this. Now, expected U3 found U64. Expected U3. Okay. And cast bucket, I guess. Where is this bucket defined? Is U64. Okay, maybe I did not need to do that. Let me just get rid of this. And we'll see. So 23. So left-hand side of shift must be fixed with integer type, or it must be comp time known. Well, as U64, 1. Does that help? Expect type U8 found U64. Okay. As U64, I guess. Sure. Now, okay. Something like this, maybe. First of all, let's do this and see. Okay. So the problem is somewhere over here. They want this right-hand side to be. No, that's fine. That's actually solved. This right-hand side here is actually of the correct size. Now, what is the problem here? Expected U8 found U64. Why would you expect that? I guess it's because value is of type U8. Okay, so let's go ahead and actually do let's just do this for now. Okay. Let's see if this works. No function name child in U7. Oh, right. Okay. That's fine. 164. Right. So I guess now I should go back and implement this for node index. Right, because so let me just redraw our thing here. So this one goes here. This one is 0, this one is 0, 1, this one is 0, 1, 2, and 3. So this child here is so the parent index times 2, this one here, and this one here is parent index times 2 plus 1. Does that hold? It does here. Times 2 plus 1. That it actually does hold. If we had another level here, we'd have something like so. And then we'll have 0, 1, 2, 3, 4, 5, 6, and 7. And then this one would hold. This one would also hold. This one times 2, this one times 2 plus 1. Yeah, it does hold. So that's what we should be using to compute the children of node index. Right. But that means that we need to put this back the way it was. Node index. Yeah, actually, I don't want to do that. So let's create a helper then. Public const node index helper is a struct that actually, never mind. Let's just do node child actually wrong language child and then here this would take self, which would be a node index. Sure, and then it would return, and of course it would take a child, which would be an enum of left or right, and it would return a node index. Right, so let's just move this where node index is defined. So it would need to be somewhere over here. Yep, okay. So that would mean we need to return, actually let me just just go up, get that, remove that, and actually we call that side, so call that side. So that would be just that, and that would be, there you go. Okay, we don't need to get parents because we don't, I don't think we need to find parents for those. So node child takes a node index and a right, and we just need to find the other ones. So node child takes node index and left. All right, let's rebuild this and see what's the problem here. Okay, we don't have value, we just have the row thing. Okay, so expected struct or union found U7. Right, so we just need to get rid of those two. And 210. Okay. Should probably just get rid of that. No, actually no. We should adapt the test. So this would be node state index. Node state index, and this one would be node state index. As well as for all of these. As well as for all of these. No. There we go. And as well as, actually, this test here we are going to duplicate. Do that. State. And then do the same here, state. So these ones, of course, this one is node state. And this one is node state also. So this test here will fail, surely. Otherwise we did something very bad. So 210, why is this failing? Node state, okay. Value is equal to 2. Okay. 2, 3, 1, and yeah, as expected, this one is failing. So we want the left child of 0, that would still be 0. Right child of 0 would be 1. Left child of 1 would be 2. And right child of 2 would be 5. I think. No. Oh, of course. So. And of course we don't have this anymore, so we need to do something like node child, and we pass it 0, something like this. Of course we should get rid of that, and we are going to just get that and get rid of, well, actually let's copy them first. So this one goes to 1, this one goes to 2, and this one goes to 5. This one goes to 0 still, this one goes to 1, this one goes to 2, and this one is right, as well as this one. There we go. Okay, so 259. Node index from pointer. U7 does not. Sure, of course. So we just get rid of. Actually, let's get rid of all values. There we go. And I guess this one here would need to have the same treatment. Okay, and these ones are easy because they're fairly well aligned. Okay, cool. So we have actually gotten there. Right, so this test here does pass now. Let's get to case 3. What would be case 3? So allocate 8 bytes. No, hold on. Allocate 16 bytes. Then allocate 8 bytes. Let me just put the case inside the brackets or braces. And let me just copy these. So here we are. Here we go. Actually, I also want to do this after the test as an indication of how well the test went. And let me just comment those out. Right, so let me make this a bit bigger. Bucket item type. You know what? I'm going to make life easier for myself. So bucket item type. Okay. So this one here, just going to format. I don't need this. And I don't need this. So try writer.print. So how are we printing this? We should do bucket item and do node something like so. Node index. And this one will be self.node index. Oops. There we go. Let's see. That should print something that's a little bit prettier. There we go. Very nice. Very nice, yes. So here we have in the so how do we go about that? Let's do something like this and I. So bucket I. Sure. Oops. Yeah. Wrong language. Fine. Yep. So in this bucket here, we've split whatever was in it. So it's empty now. Bucket 6, we have node index 1 because we've split this one to 2 and we've used 1/2. In this one here, we still have bucket index node 1 all the way to 3, where we've split off 8 bytes and we have the right child of that 8 bytes. Right, so now let's actually go ahead and add a few more things here. Let's do allocated 2. We're reallocate 8 bytes and then allocate 8 bytes more. And I'm just going to reprint the state of our buckets. Oh, okay, that's fine. That's fine, that's fine. So here we should expect this to be what? To be that plus 8 actually. Yeah. That's what we should expect. And we do have that. And as we can see, the only difference between these two states here is that now this state here, bucket 3, which had one cell that has 8 bytes in it, has disappeared since we have allocated that one. And as we can see here, we've matched the correct cell. That's pretty cool. So now let's try allocating different sizes, just to see if we still get this to play nice. So this one here should allocate that. The size should be 16, and then should get all of these. Let's call this allocate 2. Get another size. Put that there, and of course use allocate 2 here. Yes. And let's see. Oh, we do have a problem. So let's see. We are trying to allocate 16 bytes here. We should match at 7. Yeah, so we match at 7 and we are walking them back. Right. So after this step, we don't have the list at 3 because we've matched bucket 4, I think. Yeah, we've matched bucket 4. Now, we ask here for 8, and we match order 3. And so we go ahead and we walk. So what we are expecting here is that we walk up to order this one here, which should be 4. Yeah. And then we split off, or rather we take this node index from 4, node index 1, split it off, and then we get 2 nodes. So we found node at 4 with index 1, toggling its parent to false, since it's going to be... Well, that's bad, actually. 4 should not get its parent toggled, since... no, actually, it's okay. Yeah, it's okay. So we are working the node here. We matched the node here. Oh, so that's actually fine. So what is the error about? Oh, the expectation here would need to be plus 16 plus... Yeah, that should be all right. And it is. Very nice. Very, very nice. Let me just get this, put that there, put that there again, just so that we can have the buckets in front. That's very nice. So now let's test our what would be our final case for now. So case 4, and this would be allocate 8 bytes, then allocate 16 bytes. So the spin here is that we are going to first allocate the smaller size, and then we are going to allocate the larger size, and that means, that we are going to have to resplit, since we are not going to be able to just reuse a split, or the splits that are created by allocating the smaller size, basically. So here we are going to ask for 16. This one would need to be Yeah, so it needs to be 16 aligned. That's actually okay. And that's all right. So let's see. And we don't have an error, but let's see where we allocate things. So here we have the first split that's at 3 has 8 bytes in it, right? And then here we went ahead and just consumed the split that's at 4. So it went null. So 4 would give us basically 16 bytes. That's cool. That's very nice. So now if we try to add another hurdle, let's say, for our thing, let's try to allocate just 2 bytes. Let's just try to allocate 2 bytes. And these 2 bytes would need to be allocated from the first split that's created by allocating the 8 bytes. So let's see. Ooh. Expecting 16 found 2. Okay. If that's the problem, then we are golden. Okay. As we can see here, so we took the split in bucket 3, and we've resplit it to fill bucket 2 and 1, and bucket 1 has the 2 bytes since our min size is 1 byte. So now I'm going to add yet another allocation here, and I'm going to allocate just 1 byte. And that means that this one here would need to be allocated in the first split that's been used by the 2 bytes. That would need to be 8 plus 2, basically. Yeah, this one needs to be 1. Ooh, reached unreachable code. Okay. So we do have a problem.